To build a modern car body, you don't need a torch and you don't need wire. You need thousands of microscopic, instantaneous, localized electrical shorts. This process is called resistance spot welding. It is the primary joining method for high-volume manufacturing, serving as the structural backbone of automotive body-in-white assembly lines. Look at this skeletal frame. A single vehicle contains several thousand of these spot welds, holding the structural geometry together under intense dynamic loads. Unlike traditional arc welding, resistance spot welding operates under strict physical constraints. It requires zero filler metal and no shielding gas. Because the heat is applied for only a fraction of a second, the heat-affected zone surrounding the joint is minimal. It achieves this by turning the metal into its own heat source. Two copper alloy electrodes clamp the overlapping sheets, and a high electrical current, often several thousand amperes, is forced through the stack. The metal's internal electrical resistance converts that current directly into melting heat. To execute this without destroying the sheet metal requires a precise thermodynamic balance of three variables: weld current, weld time, and electrode force. This invisible microcasting process requires strict thermodynamic control over thousands of repeated cycles, ensuring the hidden liquid pool solidifies into a reliable structural bond. This diagram shows the physical baseline. We have an upper and lower copper electrode, tightly clamping two overlapping sheets of steel. The critical zone is this interface where they touch, known as the faying surface. When thousands of amps pour through the stack, the current flow is not uniform. At a microscopic level, the faying surface is rough. That surface roughness creates a bottleneck, causing the electrical resistance to spike right at the interface. This physical bottleneck is an engineering advantage. It forces the highest heat generation to occur exactly where the two sheets meet, rather than burning the outer surfaces contacting the copper electrodes. We calculate the exact energy of this localized melt using the resistive heating relationship. The formula is Q equals I squared times R times T. Here, R represents the effective resistance at the faying surface, and T is the total weld time, which is usually measured in exact milliseconds or cycles of the alternating current power supply. Once current stops flowing, the cycle enters a critical hold time. The electrodes maintain clamping force while the internal nugget cools and solidifies under pressure. The microscopic roughness of the metal itself traps the current. It turns a massive momentary electrical short circuit into a perfectly contained internal weld. Look closely at the capital I in this equation, the welding current. Because the current is squared, it is the most sensitive and volatile variable in the entire schedule. Doubling the current quadruples the heat output. This creates a narrow margin for error. A minor fluctuation in the power supply yields a massive exponential shift in the size and depth of the final weld nugget. But the electrical current does not operate in a vacuum. It is modulated by the mechanical clamping force, which directly controls the resistance variable. Zooming in on the cross-section, we see the microscopic peaks and valleys of the faying surface. When the electrodes apply mechanical force, they compress the metal, crushing those jagged edges flat. This increases the contact area and causes the electrical resistance to drop. If you apply too much clamping force, you suppress the contact resistance. The current flows right through the sheets without encountering enough friction to generate melting heat, leaving you with a weak joint. Conversely, if you apply too little clamping force, the resistance spikes unpredictably. The heat builds up too fast for the metal to contain. Mechanical force and electrical current are locked in an inverse relationship. Altering the pressure dictates the exact thermodynamic window required of the current. On a factory floor, it is tempting to lock in the weld schedule, the current, time, and force, and assume the weld quality will remain constant. That assumption ignores physical realities. The tooling takes a beating. Copper electrodes absorb thermal shocks and mechanical impacts thousands of times a shift. Over time, this repeated cycling causes a defect known as mushrooming. The copper alloy tip gradually softens, flattens out, and widens. This expansion creates a mathematical trap. Look at the left side. The machine is still outputting a locked 9,000 amps. But on the right, the tip face gradually expands in diameter. Because the surface area is increasing, those 9,000 amps are forced to spread out. The actual density of that heat at the center plummets. With less concentrated energy melting the metal, the resulting weld nugget steadily shrinks over the production run. This degradation accelerates when welding galvanized steel. The zinc coating melts and chemically alloys with the copper tip. This rapidly degrades the surface, introducing variations in electrical resistance. Trusting a static weld schedule is an operational trap. Continuous manufacturing requires engineers to anticipate this physical degradation and dynamically step up the current to compensate for the continuous loss of density. When that delicate balance of current, pressure, and density fails, the system produces specific physical defects that compromise the assembly. The most violent failure is expulsion. The internal pressure of the molten metal rapidly builds until it overcomes the clamping force, breaches the clamping boundary, and sprays liquid metal directly out from the faying surface. This happens when the current is too high or the clamping force is too weak. The molten material escapes, leaving behind a structurally deficient, undersized nugget. In a different scenario, an undersized nugget occurs entirely internally. The melt pool forms but stops expanding. It fails to reach the required minimum diameter, which is generally calculated as 4 times the square root of the sheet thickness. This is the direct result of those worn, mushroomed electrodes bleeding off the current density. The most deceptive defect is the stick weld, or cold weld. The heavy mechanical force compresses the sheets tightly, but the faying surface never reaches a molten state. The metals touch, but there is zero true fusion. What terrifies quality engineers is that an undersized nugget or a cold weld can leave a clean surface on the exterior of the sheet metal. The joint looks acceptable, entirely hiding a failure from the naked eye. The rule of resistance spot weld quality control is that visual inspection of the exterior surface cannot verify structural integrity. The automation we rely on is unthinking. A robotic arm blindly executes the code and current you give it. It cannot verify the hidden thermodynamic reality occurring between the metal sheets. Real validation demands destructive mechanical intervention. This means regularly halting the line to perform a physical peel test or chisel test on a sample run. In a successful test, the joint does not break. The base metal sheets must physically tear around the weld, pulling a solid, intact button of fused metal completely out of the opposing sheet. That torn button is the physical proof. It confirms that the molten pool crystallized into a structure stronger than the surrounding steel. Mastering this manufacturing process requires shifting focus from the macro scale of robotic arms to the microscopic arena. You have to control current density, measure contact resistance, and balance intense thermodynamics, turning a simple electrical short into an unbreakable structural bond.